For example 5, we're just going to do some examples with parametric equations. So for example 6, it says remove the parameter. That's kind of like, I don't want to say it's code, but that's kind of like the wording you'll use when they want you to convert your parametric equations back to rectangular form. So it says remove the parameter and find the rectangular equation for each plane curve. Okay? So I guess it was example 4. So in example 4, we basically solved one equation for t, substituted substituted the value for t into the other equation and simplified. Okay, so just really quick to remind ourselves, this is one method for removing the parameter and getting rectangular form of the equation. If we go back to example 4, remember we had x of t equals t minus 3. We wrote that like not in function notation, so we wrote it just x equals t minus 3, and then we solved for t, so we got that t equals x plus 3. Okay, and then we took that value for t and we plugged it into the other equation, the y equation. We plugged it in there for t, and then that gave us an equation that was just in x's and y's. So when we say removing the parameter, we're literally removing that third variable. Okay, and so example 4 is one example of how to do that. Solve one equation for t, substitute it into the other equation. Okay, down here for example 6, we're going to do it a little differently. Okay, so for example 6, what we're going to do is we're going to, instead of solving for t, we're going to solve for a particular expression. Okay, so alternate method, instead of solving for t, solve for an expression. Now, it can't just be any expression, it has to be an expression involving t. Okay, so that's what we're going to do here for example 6, part A. So again, we're going to remove the parameter, find the rectangular equation for each plane curve. Okay, so we have x of t equals 2 times e to the t power, and then we have y of t equals 1 plus e to the t power, and t has to be greater than or equal to 0. Don't let the e's freak you out. It's just a number. You've dealt with exponential equations. I mean, surely to God, you've dealt with exponential equations at some point in your algebra career. Okay, so what we're going to do, instead of trying to solve for t, solving for t would involve like log stuff. We're not going to do that. Instead, we're going to rewrite these so they're not in function notation. And we're going to solve one of these equations for e to the t power. Okay, that can be the expression that we use here. So I'm going to solve the x equation for e to the t. So what I can do here is I can divide both sides by 2. The 2's divide out on the right, leaving me with e to the t power equals x over 2. Okay, so now this value for e to the t power I can plug in over here. And what I end up with is y equals 1 plus e to the t, which we know is really x over 2. Now, that looks kind of messy, but it's actually really a nice, simple, easy equation. So let's think about this. We would be more inclined to write this early in our algebra days as 1/2 times x plus 1. So we really just get a really simple equation for a line, okay, which is kind of cool. But let's stop and think about this. We know that from the get-go, we were told, hey, there's this restriction on t. T has to be greater than or equal to 0. So that's going to tell us, hey, you know what? We're going to have some limitations on this rectangular equation here. So let's think about what this is going to mean. We have to look at the domain restriction for our rectangular equation, okay? Now, the parametric equation had a restriction, or the parametric equations. Okay, so how does this impact the rectangular equation? Well, let's think about what t equaling 0 would have been like for us. Now, when we talk about the domain restriction, we're thinking x. Okay. So we're looking for values for x such that, okay? So let's figure out what that condition is on x. So let's say t was equal to 0. So t could be 0 or anything bigger than that. So let's start with the smallest value that t could actually be, which is 0. And let's figure out what x, wrote it backwards, it's late. Let's figure out what x of 0 would have been. Okay, well, x of 0 would have been 2 times e to the 0 power. Now, hopefully you remember your exponent rules. E to the 0 is just 1. So we would get 2 times 1. So we could say x of 0 is just 2. All right, so x of 0 equals just 2. So that tells me the smallest x can be is 2. Okay, so basically, my sister used to start everything with, so basically, x can be 2 or anything bigger. And how do I know it can be 2 or anything bigger? Well, I know that basic form of like an exponential, like if we look at just e to the t power, we're going to be looking at something like this. Okay? So when t equals 0, x equals 2. Okay? So as t gets bigger, everything else is going to get bigger. So the direction we're going is kind of like up like this. So I can say, hey, as t gets bigger, x gets bigger. So we can say x can be anything as long as x is greater than or equal to 2. So that would be our restriction on x. Okay, so do be very mindful of that because sometimes you're going to be given some restriction on your parametric equations and you need to see how that's going to impact your rectangular equation. Okay, now example B, I do encourage you, I kind of have a memory of this. It's been 17,000 million years ago, 7 years at least, since I was in calculus, and I have this vague memory of these coming up. So these are important. So we have this situation where we have the parametric equations x of t equals a times sine of t and y of t equals b times cosine of t. Okay, so it's like, at what point are we going to bring trig into this? She's here. Okay, so it is time to do the trig, and we're going to do the same thing. We're not going to try to solve for t. Okay, if we solve for t, it would involve like some inverse trig functions because t is kind of like the argument here. So instead, we're going to solve for two different expressions here, okay? So let's solve for sine of t and cosine of t, okay? So let's rewrite these without the function notation. So x equals sine of t, or x equals a times sine of t, don't forget your a, and y equals b times cosine of t. And let's solve for sine of t and solve for cosine of t. So in order to solve for sine of t, I need to divide both sides by a, okay? So if I divide both sides by a, I end up getting that sine of t equals x over a. The a's conveniently divide out to be 1, and then 1 times sine of t is sine of t, okay? So that's really important. And then if I were to solve for cosine of t, I would get a situation where I had to divide both sides by b. On the right-hand side, the b's divide out to be 1. 1 times cosine of t is cosine of t. So we can say cosine of t equals y over b. Okay, now what? Okay, well, in trigonometry, we love trig identities. We love trig substitutions. Okay, so please recall, I'm going to put please here because I'm feeling extra polite. So please recall the Pythagorean is kind of like the main Pythagorean identity. It's been a minute since we've dealt with this, but it should be pretty well stuck in your head. If we have sine squared of some angle plus cosine squared of some angle, that equals 1. Okay, well, let's do it. Let's plug in values for sine and cosine. We conveniently have them up here and here. So if we take the value for sine of t, which is x over a, and square it, and then we take the value for cosine, which cosine of t, which is y over b, and square that, it equals 1. So if we clean it up a smidgen, we get x squared over a squared plus y squared over b squared equals 1, which is an ellipse. Okay, now I know it's not a hyperbola because the big thing with a hyperbola is that that sign in the middle would be subtraction. So we know it's not a hyperbola. So it really comes down to, is it a circle or is it an ellipse? It's definitely not a parabola because we have two variables squared. So let's put it this way. If A is equal to B, it would be a circle. Okay, so if whatever your value for A and B are, if they're the same thing, you're traveling the same distance in the A direction as you are the B direction, you've got a circle. Okay. If A is not equal to B, then you have an ellipse, okay? So when you see this format right here, A times sine of t, x equals A times sine of t and y equals B times cosine of t, or you could see x is A times cosine of t, y equals B times sine of t. If you see some combination like that, you're dealing with something that is an ellipse or a circle, depending on if A and B are the same thing or not. And this is common. You will definitely see this again on a very important test. All right. So with that said, let's look at the next example. Okay. So example 7 says graph the plane curve with the following parametric function and indicate its orientation. So remember, when we indicate the orientation, we need to look at successive values for t and see kind of like where we're going. So like comparing t equals 0, how does t equals 0 get you to t equals 1? How does t equals 1 get you to t equals 2? How does t equals 2 to get you to t equals 3 and so forth? So that's how we find our orientation. So don't forget, indicate the orientation. All right. So luckily, we have something that should be like extra familiar to you. We have x of t equals 2 sine t, y of t equals 2 cosine t. And notice here, a is 2, b is 2, so a equals 2, b equals 2, a equals b. It's a circle, y'all. Okay? So we're dealing with a circle, and we know this because of that previous example that we literally just did. Okay? So we're going to graph the plane curve with the following parametric functions and indicate its orientation. You don't have to do all of the work that we did in example 6, part B, but let's go ahead and do it again just to make sure we're like really good. Okay? So let's say we have x equals 2 sine of t, y equals 2 cosine of t. Let's solve for sine of t and cosine of t. So let's divide everything by 2. That tells me that sine of t equals x over 2. Let's solve for cosine of t, so we divide everything by 2. Okay, so we're going to get cosine of t equals y over 2. And then we're going to use the Pythagorean identity. Remember, don't write it like that. Remember, sine squared of theta plus cosine squared of theta equals 1. Okay, so we can say, well, if we take whatever sine is and square it, add it to whatever cosine is and square it, it has to equal 1. So we get x squared over 4 plus y squared over 4 equals 1. So this is our rectangular form. Okay, now we can do quite a lot with this, okay? We know we're dealing with a circle because A and B are the exact same, okay? So you travel the same distance in the A direction as you do in the B direction, okay? We are centered at the origin, okay? So basically we're saying A is 2, B is 2. We're centered at the origin because we have x minus 0, y minus 0 squared. You go to the left, right, up, and down 2. Okay, we know this in the rectangular world, but let's practice what this means in the parametric world, because what we need to do is we need to find the orientation, which means what is the direction we're traveling this circle. Okay, so let's do, where's my mouse? Let's do just kind of like that table of values with t, but remember, we have to think about what t is going to be here. Okay, so we've got t. We have x equals 2 times sine of t. We have y equals 2 times cosine of t. And then we have points on this plane. All right, so keep all that in mind. Okay, So let's see here. We're going to choose really special values for t. We're going to choose easy values. So we're going to look at when t is 0, pi over 2, pi, and 3 pi over 2. So those are, let me, well, I can kind of scoot that down just a smidgen. Yeah. Okay. So let me scoot this one down just a little bit so it's not quite so scrunched. Okay. So we're going to look for these really nice values for theta, which is really what our t is, because when you think of sine and cosine, your input is some angle. So we're letting t be some angle. Okay. So we're choosing very specific values for t that are easy to work with. We want those zeros and those ones. Okay. So kind of envision your unit circle sort of off to the side somewhere. Okay. In fact, I'm going to put my little unit circle down here. Okay. So we have our unit circle. We have the point 1, 0, 0, 1, negative 1, 0, 0, negative 1. Pretend that's a beautifully drawn unit circle. Okay. So we're going to plug in 0 here. So sine of 0 is 0. 2 times 0 is 0. So sine, 2 times sine of 0 is 0. Okay. Now cosine of 0 degrees is 1. 1 times 2 is 2. So we get a point on the plane 0, 2. Okay. Now we're going to do the same thing, but we're going to plug in t as pi over 2. So we're now up here. This is pi over 2 right here. Okay. So sine of pi over 2 is 1. 1 times 2 is 2. Okay. Cosine of pi over 2, remember, we're up here. We're looking at this point right here in red. So cosine of pi over 2 is 0. 2 times 0 is 0. So we get the point on the plane, 2, 0. Okay. Now we're going to look at pi. So pi is this point over here. Let's do green. Okay. So we're looking at this green point. So sine of pi is 0. 0 times 2 is 0. Cosine of pi is negative 1. Negative 1 times 2 is negative 2. Remember, we're just doing basic function notation, but the value we're plugging in for t just happens to be a theta value. Okay, so we get the point on the plane, 0, negative 2. Okay, and then for 3 pi over 2, that's going to be this point down here in blue. Okay, so when we do that point in blue, well, sine of 3 pi over 2 is negative 1. Negative 1 times 2 is negative 2. Okay. And then cosine of 3 pi over 2 is 0. 2 times 0 is 0. So we get the point negative 2, 0. So let's really think about what this means. So let's think about when t equals 0 degrees. So when t equals 0 degrees, we get the point 0, 2. So this is when t equals 0. Okay. Now, next iteration is pi over 2. So when t is pi over 2, we get the ordered pair 2, 0. Okay. And then when we have pi radians, we get the ordered pair 0, negative 2. So this is when t equals pi. And then finally, when t equals 3 pi over 2, we get the ordered pair negative 2, 0. So this is t equals 3 pi over 2. So let's draw our circle. Let's pretend it's a circle, okay? But from t equals 0 to t equals pi over 2, we were traveling in this direction. And then from pi over 2 to pi, we're following that direction still. And then pi, did I skip one? Yeah, and then pi to 3 pi over 2, we're that same direction. So that's how you find your orientation. You need to find successive values of t. 3 or 4 is plenty, and then that'll, well, I don't want to say plenty, but for the ones we're going to do, 3 or 4 is plenty, and that'll give you the orientation, which remember is just the direction we're traveling. So it gives you that definite starting point and then the direction. Okay, so there you have it. That is, we found the rectangular form. We didn't really have to have it. I just wanted you to get practice finding that rectangular form. It also helps us verify, hey, we're dealing with a circle here, okay? And we know that because A and B are the same, we're traveling in the same direction, or we're traveling the same distance in the A direction as we are in the B direction, which gives us that circle. Okay, so there you have it. That is graphing a plane curve with the following parametric functions specifically indicating orientation. Okay.